All right, so today we start Unit 6, Chapter 6, and we're going to talk about discrete random variables today. So, a random variable in general is a numerical. So, we need our data to be numbers. It's a numerical measure of the outcome of a probability experiment. Which means that if it's a random variable, that the value needs to somehow be determined by chance. So that's what makes it a probability experiment. Within types of random variables, we have discrete random variables, which is what we're focusing on in this section, as well as continuous random variables. So a discrete random variable has a finite or a countable number of values. So one way to think about a discrete random variable is if you were to graph it on a number line with, here's our different values. On a discrete random variable, you're going to have just individual dots like 0, 1, 2, 3. With a continuous random variable, it has infinitely many values. And so it doesn't necessarily have to be, these numbers themselves, but let me try to change the color here for a second. If I were graphing a continuous random variable, its graph would look more like this. So again, it doesn't have to be between 0 and 3. It could be between 0 and 150, 0 and infinity, actually. But when we graph a continuous random variable, it's going to be uninterrupted. So all of the values between there, whether they're radicals, whether they're fractions, whether they're decimals, whether they're whole numbers, if it's a continuous random variable, it's going to have all of those values in there, an infinite number. A probability distribution looks sort of like what we had with setup of frequency or relative frequency tables. But the way that it's set up is that it has the possible values of the random variable in one column, and then their corresponding probabilities in the other column. In order to be a discrete probability distribution, in addition to the fact that it has to be a random variable, so meaning it has to be numerical where it's from a probability experiment. So the other things that have to be true are that the sum of all the probabilities has to equal 1, which we've talked about that before, because we know that 1 means 100%, so that should cover all the outcomes. And then each individual probability needs to be between 0 and 1. So P of X is the probability that the value is lowercase x. When we use random variables, we typically, and I'll write this up here, use capital letters to represent them. So notice that's true here. We're saying the random variable is capital X, but the value of that random variable is lowercase x, because that's what will change as we go. We're also going to look at some graphs of discrete probability distributions. So sort of like what you would do with a bar graph, you're going to, on the horizontal axis, just have each of the individual values. But instead of drawing a bar on a discrete probability distribution, we just draw a vertical line, and the y-axis is the probabilities. So we just draw a vertical line up to the appropriate height. So these next two formulas are going to be really important for you because you will be asked to calculate the mean of the random variable and the standard deviation of the random variable by hand. So we'll do an example of these, but you do need to know how to do this by hand. I'm going to show you how to check it with StatCrunch, and then obviously there are some practice problems where you've got rather large data sets. Where those ones, if it's got the little, data mark next to the problem number in the homework, then you're allowed to exclusively use StatCrunch because this would be very time consuming for a large data set. All right, so I've got the StatCrunch directions here, and I will show you that here later in the examples as well. So the other thing that's true about the mean of a discrete random variable is that the mean also represents what we would expect to happen in the long run of this values of this random variable. So another term for the mean of the random variable is the expected value. So these are one and the same. They mean the same thing, but you need to know that that's what the expected value is. That when you're asked to find the expected value, you're really just using this formula here, the sum of all x times p of x. So remember, x is each individual value times its probability, and then we just add those all up. For the standard deviation, you can see the calculation slightly more complicated, but I'll show you how to do that as well. So let's get into our examples then. So example 1, determine whether the random variable is discrete or continuous. In each case, state the possible values of the random variable. So first one says the time it takes to fly from New York City to Los Angeles. So back when we talked about data in general, the kind of rule that I said was your go-to. Sometimes we have to think a little bit more than this, but discrete versus continuous, is it counted or is it measured? If it's counted, then it's typically discrete. If it's something that's measured, that's typically continuous because there could be infinitely smaller units of measure. So time is measured because we could measure time in hours, or we could do minutes, or we could do seconds, or we could do milliseconds, nanoseconds, so on and so forth. So we can just make our units smaller and smaller and smaller. The values for time would not be countable. So this is going to be a continuous random variable. So we'll write continuous. Then it says state the possible values of the random variable. So whatever variable you want to use for time. So we know time can't be negative, so we're going to start time, and it can't be exactly 0. We know that it's definitely going to be larger than that, regardless of what unit you're using. So here you might say, well, I know that the flight is about this many hours. Well, we might not be measuring in hours. So we're going to say that in this case, our time is going to be greater than 0. Again, depending on the specific unit we use, we might be able to be more specific about that, but we're not specifying. It doesn't say the time in hours it takes to fly. So we know it might be really, really large if we're measuring, in milliseconds or something like that. So can't be exactly 0, can't be negative. So we're going to say that the possible values are that our random variable value needs to be greater than 0. Part B, the number of light bulbs that burn out in a room next week in a room with 20 bulbs. So Most of the time, your light bulbs don't burn out super quickly. So this says in the next week. This is making, forcing us to have a value. Number of light bulbs is something that we count, not something that we measure. So that part makes it discrete. Now, if we're actually trying to figure out how many light bulbs might burn out in the next week, it has 20 bulbs. It's possible that no bulbs could burn out. So when I go to list my values, I could start with 0, or it might be 1, or it might be 2. Now, like we talked about here, you do have an upper limit. You are not going to replace a light bulb in one individual light faster than a week. So I would say that the upper limit here, when I'm looking at this, would be 20, because it's very unlikely that you would have to replace all 20 bulbs, but it's possible that, you put them all in at the same time and now suddenly they're all burning out in the same week. Again, very unlikely, but possible. You are not going to have the same light bulb burn out more than once a week. Light bulbs typically last for months. So we would say that our values are our counting values. We've got commas, don't include anything in between. It's just the individual numbers, 0, 1, 2, all the way up to 20. Part C, the amount of snow in Toronto during the winter. So you think to yourself, is amount of snow something that I count, or is it something that I measure? And in this case, the amount of snow is something that you measure. So that means that this is going to be continuous. So for our amount of snowfall, it's possible that it could snow none in Toronto during the winter. Not likely, but it is possible. It's not an impossible event. So we'll just use S to represent snow, I guess. There, again, could be an upper limit, but we don't know what unit we're measuring in. Are we measuring in cubic centimeters? Are we measuring in cubic meters? That matters. So we can start at 0 and go up from there. So all the way up to an infinite number. Notice that these were both continuous random variables. This one had an equals and this one didn't. So each time you are looking at continuous, you do still have to think about, where would I be starting? Is there a, set upper limit for that? All right, example 2, the table below shows the number of times that a newborn baby's crying wakes its mother after midnight in a week. So we've got 0 through 5, waking after midnight in a week. And these are the individual probabilities, the individual probability of 0 being very low, and obviously working its way up from there. So part A asks, is this a discrete probability distribution? Explain. So these are our two values. This is a discrete random variable, so I'm good on that part. The other things that have to be true is that I need the total probability to add up to 1. So I'm going to add 0.04 plus 0.22 plus 0.46 all the way down through the table. And when I add those, I do get 1. So each individual probability is also between 0 and 1, so we're good on that. So we would say yes. For our explanation, we would say the sum of all p of x equals 1, and each individual p of x is between 0 and 1. So it meets the requirements, and we're good to go there. Part B, find the mean and the standard deviation by hand. So the mean is not terrible. You are just, as the formula tells you, you're going to do the sum of all x times p of x. So I'm going to write that out to the side over here. So for each x times p of x times p of x, well, 0 times anything is 0, so we're good there. 1 times anything is itself, so those first two are super easy. A lot of these, you can see you don't even need a calculator for. You can double 0.46 pretty easily as well. So that gives us 0.92. Then we've got 3 times 0.18, which gives us 0.54. We've got 4 times 0.08, which is 0.32. And then finally, we've got 5 times 0.02, which gives us 0.1. So this is x times p of x for each individual value of this discrete random variable. So to find the mean, I would need to add all of those up. So finding the sum, so 0 plus 0.22 plus 0.92, so on and so forth. So we're going to add all of those together. And I'm going to double check myself here because we don't want to have any typos. So I've got 0.1 plus 0.32 plus 0.54 plus 0.92 plus 0.22, which gives us 2.1. So that means, and notice, remember, notation is really important. They expect you to know the notation. This is the notation that we use. So this is the population, so we're using mu, but it's the population of the discrete random variable, which would be capital X, because individual x's are the values. So this guy is 2.1. There's our mean. We found it by hand, so you would need to show some sort of work for these in your homework, unless it has the little, data symbol next to it. If it has the data symbol, then it's okay to go ahead and do it exclusively in StatCrunch. But otherwise, you need to show your work in some manner. It doesn't have to be, writing out with a table. You could just write 0 plus 0.22 plus whatever. Now we're going to do the standard deviation. That I would recommend a table, so it's up to you. As long as I can follow your work, it doesn't matter to me, but I would suggest making some extra columns and using a table. So what we need is the sum of all x squareds times p of x. And then we need the mean of the discrete random variable as well, because we're going to square that, but we've already got that part done in the 2.1 here. So first thing I'm going to do is I'm going to fill out my x squared column, which of course you don't need a calculator for. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. So we've got all our x squareds. Now I'm going to make a column for the x squared times p of x's. So notice now these are right next to each other. So p of x times this guy is how we're getting this column over here. So notice I start off the same as I did with x times p of x because of the nature of 0 and 1. So then I've got 0.46 times 4 this time. So that's 1.84. I've got 0.18 times 9, which is 1.62. 0.08 times 16, which is 1.28. And then 0.02 times 25, which is 0.5. So these are the x squared times p of x values. So I need the sum of all of those. So 0.5 plus 1.28 plus 1.62 plus 1.84 plus 0.22, and then obviously plus 0 isn't adding any value. That gives us 5.46. So when I go to calculate the standard deviation, if I look back up at the formula, I have the sum of all x squared times p of x. I know what mu sub x is, so this is all under the square root. I've got the square root of my 5.46 minus the square of that mean. And again, it's all under the square root. So 5.46 minus 2.1 squared gives me 1.05. And so then I square root that, which gives me 1.02. So my mean here is 2.1. My standard deviation of the random variable x is 1.02. So these would be my two solutions there. So now you know how to do that by hand. We also want to be able to answer some questions, and I'm going to show you how to do this in StatCrunch as well. But when you're given the table, it's not too hard to do without StatCrunch. Would a newborn baby that wakes its mother after midnight 4 times a week be considered unusual? Remember that unusual means, is it significantly high or significantly low? And remember that the probability marker for that is 0.05. So is the probability of what they're asking about less than 0.05? If it is, then we would say it's unusual. If not, then we would say no. So 4 times a week is 0.08. That's not less than 0.05. So we would say no, because the probability of x equals 4 is 0.08, which is greater than 0.05. Now, along these lines, make sure you read the questions carefully, because it might say 4 or more times, which would, obviously mean we would need to add. In this case, the events itself are mutually exclusive, so we wouldn't have an and situation. But make sure you read carefully to know which probability it's asking about. All right. Next, I'm going to show you how to do these calculations in StatCrunch. So I'm going to go back up so we can see the directions here. So you can use StatCrunch to check your work by just typing this table into StatCrunch by hand if you would like. I am pulling up the data from number 17 in the textbook, which is not one assigned to you for homework, but this is just data that's already in there for us. So it tells you to name the first variable x and the second variable p of x. Right now, this has an actual name of the random variable. That's up to you. It's number of televisions. You can change that to x if you want, but this is the number of televisions in a particular household, and then their individual probabilities. So as long as you know what the random variable x is standing for, you don't really need the title there, and it makes it a little bit easier to deal with. So I've got my data in here, so then I look at my directions. Oops, moved them over. I've named variable x and then p of x. Then we go to stat, calculators, and custom. So we're very fancy here. Stat, calculators, and custom. Then it tells us, it doesn't tell us, we tell it. It's saying, where are my values and where are the weights? Weights like weighted grades, so probabilities are the weights. So my values are in X, my weights are in P of X. We've briefly looked at how to use this build. We don't need that here, but just so you know that there are additional options that you can explore in there if you ever wanted to just play around. If I hit compute, it shows me the graph. So remember how I talked about that each individual value of the random variable would have a vertical line. Notice that this is P of X. It says F of X, but we know that this is the probability. So the value 1, the value 2, the value 3, so on and so forth, you can see their individual probabilities by the height. Down here, it tells me the mean of that discrete probability distribution as well as the standard deviation. So here is where you can check your work. Here is where, remember the question where I said, is it unusual? You can type those in here. So you could do a strictly equals, like the other question said strictly equals, to 4. Obviously, this is different data. But you can manipulate these how you want, and notice that it's changing the probability. So less than, is different than less than or equal to. So you can look at the probability of the discrete random variable having a certain value or being below or above a certain value, and this box right here can tell you whether it's unusual or not. All right, so this is a great way to check your work. I would encourage you to check your work in StatCrunch so that you get used to it. The more you use StatCrunch, the more comfortable you become with it. So please make sure you practice on more than just the ones that have that data symbol next to them in the homework. All right, so the very last thing then, example 3. Suppose you are playing a game with a biased coin. So this is not just a regular coin, it's weighted in a specific way. You play each game by tossing the coin once. The probability of heads is 2/3. The probability of tails is 1/3. So this is what tells us it's weighted, because typically we would have 1/2 for both. If you toss a heads, you must pay $6. If you toss a tails, you get $10. Find the expected value. So expected value, we had underlined that up here when I was going through the definitions. Expected value is the mean of a discrete random variable. Now in this case, we're not given a chart. That doesn't mean that we can't make one. We don't really need one here because there's only 2 possible outcomes. And expected value, we take the value times its individual probability. So in this case, when we are looking at the values, the value is the money. The value isn't heads and tails. Remember, the values have to be numerical to be a random variable. So the values of X are pay $6 and get $10. The probabilities are the 2/3 and the 1/3. So when I go to do the expected value, that's really just the same as calculating this guy. So I take the individual expected value, pay $6. Now pay $6 means you're losing $6. So the value is actually a -6. Then the probability of the value being -6, because it's heads, is 2/3. Remember that mean is the sum of all X times P of X. I have X times P of X for the first outcome. I have to add in my other outcomes. In this case, there's only one additional outcome. Get $10, that's a positive $10, times the probability, which is 1/3. So when I calculate that, so I do -6 times 2/3, which is -4. Ooh, stray mark there. Sorry, I'm going to scribble that out. -4. And then we have 10 times 1/3. So 10 divided by 3 is about 3 1/3. So 3.3 repeating. So what we get for our expected value is, and we're talking money here, -0.6 repeating, which when we're talking money, we do rounded to the nearest cent unless they tell you otherwise. So my expected value is -67 cents. So yes, it can be negative because that means you're losing money or owing money. So again, I want to make sure you understand what this answer represents. What this is saying, the expected value is what we would expect to happen over the long run. Long run meaning if I sat there and played this game 3,000 times, overall, what would I expect to happen? I would expect to come out losing a little less than $1. So if we applied that law of large numbers, we would end up still down money. All right, so hopefully this makes sense, and I'll be happy to answer questions when I see you again in person. Make sure on the homework you can stop at 30. So I think it originally said 38. But the homework assignment is 1 through 4 all, and then 6 to 30 even. Stopping there still gives you plenty of practice with all the different types of problems. I don't think that the ones after that are needed for you to understand the concepts. So let me know if you've got questions and get to work on those problems.